Okay, welcome to 1.3, Displacement in 2 dimensions. We're going to be talking in this lesson about 3 different methods you can use to solve two-dimensional problems, specifically two-dimensional displacement problems. So we want to determine a total displacement, and the first thing is a displacement vector has, of course, two important parts, magnitude and direction. Okay, and direction, you probably remember that we write things like west 35 degrees north to represent a direction. Okay, so this example on the left here, that's west 35 degrees north. Now we have 3 methods, as I said, for determining the displacement. The first one here is a scale diagram, and we're going to look at all 3 of these. So scale diagram. Number 2 is the cosine and sine laws. And number 3, which is really going to be, once you've seen all 3 methods, number 3 is going to be the one that we focus on for the rest of the course. So number 3 is called the perpendicular components method. Okay. So, we'll start with the scale diagram method. And for this method, what we do is you draw the vectors using a ruler, a protractor, and a scale. And by a scale, I mean just a statement that says for every 1 centimeter I draw, it'll be 1 kilometer in real life, or something like that. A scale looking something like 1 centimeter to 1 kilometer. That sort of thing. Okay. So that's what we're talking about with the scale. And so we need these. The other piece of this is that we're going to connect the vectors tip to tail. And that means that when we draw each subsequent vector, when we draw each subsequent vector, the next vector's tail, or the end of it, connects to the front of the previous vector. This is called tip to tail method. Okay, so we're going to try doing a scale diagram here. It says, suppose you walk to a friend's house taking a shortcut across an open field. Your first displacement is 140 meters east 35 north across the field. Then you walk 200 meters east along the sidewalk. Determine your total displacement using a scale diagram. Okay, well, scale diagram, we need to get out our ruler. And for me, I need to use this funny looking software ruler. But for you guys, hopefully you have a proper ruler at home. And you also will need a protractor, something that looks like this. And if you don't have one of these, well, I recommend getting one. You can get one in most geometry sets, along with rulers and that sort of thing. But we're not going to be using these a lot. In fact, really just in this lesson. So if you don't have one, don't worry too much. Okay, I'm just going to shrink this down a bit. Okay, so what we do here is we want to create first a vector that's, well, we'll create a starting point first. So let's say that I'm starting down here. And the next thing I need to do is I need to define my directions. So I can say here that north is up. And the next thing I need to do is define a scale. So for me, I'm going to use a scale of, what do I want to use? I guess I will use 1 centimeter to 100 meters. So that means that my picture is actually going to be, well, You know, I think that's going to be too small for my scale. So I guess I will try 1 centimeter to 10 meters. And let's just try that. Let's see what we get to. I'm hoping that I can sort of fit the whole picture into this space that I've given. Okay. So I'm going to start down here. I know that I start by moving 140 meters east 35 north. So that means that I need to get my ruler on an angle of 35 degrees. And it's kind of handy because my software tells me what angle this is at. So now this ruler is at 35 degrees. But if you were using a real ruler, what you would do is you would get your protractor, you would line it up with this dot, and then you would say, well, I want 35 degrees, so we've got 10, 20, 30, 35, and I can put a little dot right there at 35. And so then I move that away, I take my ruler, I line it up with those two, and you can see that my ruler already does line up with those quite nicely because it's set to 35 degrees. Okay, so I line up my ruler, and then what I want to do is I want to draw a line that's 140 meters. So using my scale, that would be 14 centimeters. And look, that's really not going to work because that goes all the way up into the page above. So I'm going to change my scale one more time. And I'm going to say that 1 centimeter is equal to 20 meters. So now I just need to make one that's 7 centimeters long, and I can do that. 7 centimeters I can handle. So I draw a line, 7 centimeters long. Good. And I want to make sure that I've got the arrow on there. Okay, part 2, it says 200 meters east. So I need to rotate this back so that it is level at 0 degrees. So perfectly horizontal. And now I will draw another line. I'll line up my 0 here. 0. Good, and I will go 200 meters, so it means it's going to be 10 centimeters on my ruler using my scale. So 10 centimeters, there we go, there we go. And I'll draw my arrow. Okay, so the last piece here is I've drawn those two. Now what I want to do is figure out the total. Well, the total is going to be the distance from the starting point to the end. So what I need to do is a couple things. I need to extend my ruler, and I need to rotate it. And this step is probably going to be easier with the real ruler than it is with my software ruler. Okay, that's looking pretty good to me. So I want to measure how long this is. I'll set up the 0 at the start, the bottom left. And it looks like I've got about 16.3. Seems to be about right. So I'll draw this total line here. I'm going to say that's about 16.3 centimeters long, which now, if I convert that back into my correct units, I need to multiply by 20. So that gives me 20. Let's see. It gives me 326 meters. Okay, so that's the length, and then the last piece is I need to figure out what that angle was. Whoops. So I bring my protractor over, I line it up with the dot, making sure that the bottom edge is horizontal, and I can see what angle this is. So let's see, it looks at about, counting up from 10 degrees, I've got 10, 11, 12, 13, 14 or 15 degrees. So let's just say that that's 15 degrees. So this is about 15 degrees here. So that means that my answer is 326 meters east, 15 degrees towards north. That's my total displacement. Okay, and if I made some mistake, I'm sorry, but that should be about right. Alright, I'm just going to get rid of these rulers now because we're done with that. That's the graphical way that we can solve these problems, and I think for most of our purposes it's not great. Because you'll notice that it took a fair bit of time, you have to be pretty precise, and the answer that you get is maybe not very accurate. It's not as good as doing math on the numbers and getting a more precise answer. So now we're going to look at method 2. That was method 1 here, method 1. Now we look at number 2. Number 2 is using the cosine and sine laws method. So here what we want to do is we sketch the problem. Then we use trigonometry, to solve the triangle. Now the only problem with this method is that this only works for two vectors, for adding two vectors together. So if I have 3 vectors, or 4, or 5, or 10, I can't use this method. It only works with 2 vectors. But we'll take a look at how that does work. So first up, I want to sketch my, my situation. So let's see. I drew it properly up there, so I know about how it looks. The sketch looks something like this. Okay, and my values here, I had 140, 200, and we don't know what this side is. We're trying to solve for this final side, so this is going to be my total displacement. Okay. So, some bits of information. We know that this angle all the way to the ground, or all the way to the horizontal, well, that is going to be 35 degrees, because we're working with east 35 degrees. So that's 35 degrees, which means that this angle just on the inside, well, that's got to be, well, again, I guess we don't necessarily know what that is. What we do know is that if that one was 35 down there, then this one up here also has to be 35 degrees. That tells us that this angle is 145. And now we have enough information to solve this triangle because we have two sides and the angle in between them. So we can use the cosine law. Hopefully you remember the cosine law from your other math classes. It looks something like, we'll say this here, looks something like c squared equals a squared plus b squared minus 2ab cosine and then the angle of c. So now if we're trying to get c, which is, we'll say it's our displacement here, well, looks something like this. C squared is equal to, and I've got my two sides, 140 squared plus 200 squared minus 140, 200 times the cosine of my angle, 145 degrees. Okay, and so this is how we're going about solving this problem here. So we've got c squared, so now c is going to equal the square root of that. And I'll just go ahead and find that number. The number of all those added together is 105,473. Okay, so that means that c is equal to 324.8 meters. Okay, so that gives us the value of our displacement. We've been using c, but really c was representing our total displacement. But we don't actually know the direction yet. So we need to do some more math. This has just given us the magnitude. Okay. So now to get the angle, we're going to need to use, this was all using the cosine law. Cosine law. And now we're going to use the sine law. So what we can say is this angle here we're trying to find is, we'll just call it theta. And we can say that sine theta over its opposite side, so 200, is equal to sine 145 over its opposite side, which is the value we just calculated, 324.8, which tells us then that theta is equal to the sine inverse 200 sine 145 over this guy. Okay, so now you can just plug that into your calculators and we get theta. Theta is equal to 20.7 degrees, which tells us in the end that therefore our total displacement is equal to 3 I'm just looking at the units here. So we have 3 significant digits in the numbers. So we've got 324, not 324.8, but we'll say 325. Oh, and I'm just noticing that our degrees are only 2 digits, east 35 degrees north. So I'll round this here. We've got 320 meters going now. Finally, we need to find our angle, and I've got our angle here, theta, but what we actually want to find is this angle here from east. So we can say that the total angle is 35, and theta comes out of that, so our angle, we're not quite done here, our angle was 35 degrees minus 20.7, which is equal to 14.3 degrees. So finally, we have east 14.3, or in this case we're going to round, east 14 degrees north. Okay, and there we have a final answer. And you can see that this is maybe not the best solution either, the best method, because there was a lot of sort of difficulty, especially with this angle at the bottom here, figuring out what that is. So we're going to look finally at decomposition, or using perpendicular components, and this is, in my opinion, by far the best method. It works with any number of vectors, it's very straightforward, and it always gives perfect answers. So, perpendicular components, the idea here is that we break each vector into perpendicular components. And we'll say into 2 perpendicular components. Then we add. So we get the x component, we get the y component, and then we add the x, we add the y, and then total the end. So we'll see in the bottom here exactly what we're doing. There's an example to the right. We've got this vector, we've got it drawn here, and we break it into a vertical component and a horizontal component. So those are 2 perpendicular components, and we find those using sine and cosine. So you can see here that if I'm breaking it up this way, if my angle is on the bottom here, then the opposite is going to be d sine theta, and the adjacent edge is going to be d cosine theta. So we'll write that here. The x component of our vector, as long as our angle is given here and not up here. If we write east 37 degrees north instead of talking about north something degrees east, then we can say this, that the x component is equal to the magnitude of our displacement times the cosine of theta, d cosine theta. Okay, and same with the y component here, dy is equal to magnitude of the displacement times the sine of theta. And I'll just warn you that the cosine and the sine will swap if the angle is measured from the vertical rather than the horizontal. So you can see what I mean is that this angle is measured from the horizontal. So we're saying from horizontal we go up 37 degrees. If instead we said from vertical we go down 53 degrees, then sine and cosine need to swap there. Okay. So, we'll look at one example first of just what this is, how we can break something into components. So it says a polar bear walks towards Churchill, Manitoba. The polar bear's displacement is 15 kilometers south 60 east. Determine the components of the displacement. So here we're going 15 kilometers south 60 degrees to the east. So what we're saying here is that we've got from south we went over 60 degrees. I haven't drawn that very well, so I'll just clean that up. Because if we're talking 60 degrees, we're looking more like a triangle like this. Here we have 60 degrees, and we're told that this is 15 kilometers. Okay, we want to determine the components. So this is the total displacement, and this is the x component, and this is the y component. Okay. So if we want to get those components, again, using this angle, I'm just going to start by looking at cosine and sine. So I can say cosine of 60 degrees is equal to opposite over hypotenuse. So we have displacement x over the displacement. And you know what, I'm just going to take out the vector arrows here because we're just talking about the magnitudes here. So displacement x and displacement. Okay, and so sine 60 degrees is equal to displacement y over the displacement. Okay, those two things can be rearranged. This solves for me displacement x is equal to displacement cosine 60, and here displacement y, displacement sine 60. If you plug your values in there, you should get 7.5 meters south, and you should get 13 meters east. Okay. Now at the bottom here it says adding vectors algebraically. So we're going to leave this, we're going to look at this together in class because I haven't given you enough space here, I haven't given us enough time here, so I want us to look at this together in class, which we will have a chance to do. Okay, so I hope you followed all of that. If you want, you can look at the homework, but again, we'll have time for that in class as well. So enjoy that, and see you in the next lesson.